In calculus, the limit process answers the question, what happens to f of x as x approaches a particular value? And how is this different from the simple substitution that we learned in Algebra 1? Hi, my name is Dr. Ron, and welcome back to my channel. In this video, we'll explore what the limit is and exactly what it does for us mathematically. Let's get started at looking at limits. An everyday example of the limit is the speed limit. Here's some dashcam video of me driving through my neighborhood. Notice that the posted speed limit is 30 miles an hour, or just under 50 kilometers per hour. It's important that we not exceed the speed limit to avoid getting a traffic ticket, or more importantly, to avoid having a traffic accident. We can think of the speed limit idea as a kind of border or point that we can approach from above or below. We can apply the same idea to a function. Consider the graph of y equals x shown here. In Algebra 1, we learned that we can just plug in the number 1 to get the value of y at x equals 1. In other words, this. We can apply the same idea of the limit, but in this case, we're not asking what is the value of f of x at x equals 1, but rather, what value of f of x do we get close to as x approaches 1? And that approach can be from either side, from the left, also known as below, or from the right, known as above. The calculus notation we use to indicate the limit is the first 3 letters of the word limit, LIM. We write a little x and an arrow pointed toward the right to indicate the limit as x approaches 1. So I'll write that. And here we're going to just go ahead and use our notation f of x. We could also substitute the actual expression for f of x. In this case, f of x equals x, or y equals x. And we can see that as we approach from the left or the right, we're going to approach that value 1. And this is exactly as we expected from Algebra 1. Now, regarding the approach from the left or the right, I can write the approach from the left, in other words, from values of x that are less than 1, for example, 0, 0.5, 0.9, even 0.999, by adding a little negative sign as a superscript to the right of the 1. Again, we can write the expression for a function x, and we can see from the graph, as I approach from the left, we are going to get close to the value of 1. We call this a left-handed limit. Likewise, there exists a right-handed limit. Again, we're going to write LIM, x, arrow to the right, 1, and we're going to write a little plus sign. And again, we see for a right-handed limit that we are also approaching the value of 1. The left-handed and right-handed limits are called one-sided limits. In order for an overall limit, this top one, to exist, the left-handed limit must equal the right-handed limit. We'll have more to say about left-handed and right-handed limits and how they affect what's known as continuity of a function at a point. This is a very important concept for calculus going forward. I'd like to show an alternative notation that I have seen in the past. It's not as common anymore as the little minus or little plus, but I just wanted to point it out so that you're aware of it in case you see it in some other texts. Some authors use an arrow pointing up, indicating that we are using values of x that are increasing toward the value of 1. For example, from 0 toward 1 with an up arrow. That's another way of writing a left-handed limit. Likewise, an arrow facing down or pointing down of x indicates a right-handed limit. I will not be using this notation throughout these videos, but I just wanted to make you aware of their existence. I've redefined this function as a piecewise function where the value of the function at x equals 1 is not defined and therefore does not exist. Again, if we use our algebra 1 concept of plug and chug, if I try to plug in x equals 1 into the function, it is a DNE or does not exist. However, the limit as x approaches 1 of this function f of x still equals 1. Notice that if I approach from below or the left-hand side, I'm getting closer and closer to f of x equals 1. And as I approach values of x from the right-hand side, getting smaller and smaller, getting closer and closer to 1, the value of f of x also equals 1. We say that the left-handed limit, the limit is x approaches 1 of our function x equals 1, and the right-handed limit, the limit as x approaches 1 from the right also equals 1. Something that I will do in this video series is that I will often write these 3 dots to mean therefore. And so if I write that, it's therefore. Therefore, because the limit as x approaches 1 from the left of our function equals the limit as x approaches 1 from the right of our function, we can say that the overall limit as x approaches 1 of x equals 1. And this is true even though the point f of 1 does not exist. Here's the same concept for our piecewise function, which is not defined at x equals 1, written out as a familiar algebra 1 type t-table. Again, we note that at the value of x equals 1, f of x doesn't exist. However, I can determine the limit as I pick values of x increasing from 0.5 just very close to 1.000. I pick 0.999. You can add additional 9s if you wish, but I think you'll get the point. As I approach 1 for x from the left, I get very close to the value of 1. Likewise, I can go down in value for x from 1.5 to 1.1 to 1.01, and you can see once again the values of f of x are getting very, very close to 1. This is true even though f of 1 does not exist. We can write, therefore, that the limit as x approaches 1 overall of f of x equals x for this piecewise function is going to equal 1. So the limit exists even though the point f of 1 does not. That's the difference between our algebra 1 plug and chug and the concept of the limit. When you're going to fill out a t-table, either on one of your teacher's exams or on an AP exam, be sure to write the x values in increasing order as though you were filling out a number line. It's important to do that because we need the number line idea of increasing values to illustrate the left-handed and right-handed limit ideas. You don't want to write 1.5, 1.1, and 1.001 like that. That simply doesn't make sense. Likewise, we can see the values of f of x for this particular piecewise function. It happens to be an increasing function, increasing as well, and this is also a number line. Indeed, the Cartesian coordinate that we all use, the xy plane, is nothing more than two number lines that are at 90 degrees to each other. We've already seen the result that when y equals x, the limit as x approaches some value a, be it positive or negative, is going to equal that value. In other words, we can simply plug in a for x. That's true, again, for when y equals x. When y equals a constant, for example, I pick 2 in this instance, notice that it doesn't matter what value of a we pick along the x-axis. If I pick a equals 5, y is going to equal 2. If I pick x equals -1, y is still going to equal 2. Consequently, we can say that the limit as x approaches any value a on the x number line of a constant function c, in this case c equals 2, well, that limit is going to be the constant c, in this case 2. Finally, a familiar function is y equals 1 over x. By the way, as an aside, if you're studying calculus, be it AP Calc or at a college or university, I highly recommend that you go through and be able to sketch some of these basic functions. Oftentimes, the answer to a question is either within that basic sketch or can be derived or figured out from the sketch. Here's a sketch of 1 over x. Notice that the limit from the right-hand side as x approaches 0, again from the right, while I'm heading toward that vertical asymptote or positive infinity. Likewise, I could approach from the left, and I see that as x approaches from the left, f of x or y approaches negative infinity. Because the limit from the left of this function does not equal the limit from the right, we can conclude that the overall limit as x approaches 0 of 1 over x does not exist. We'll be using these three results going forward. Click on this link if you'd like to learn more about limits and how to use them, and click on this link if you'd like a review of calculus and what it's about. I'll see you in the next video.